Today's speaker is Jonathan Perry-Houts, and he'll be talking about numerical models of the lower crust flow explained to explain Yellowstone's tectonic parabola. Jonathan received his PhD at the University of Oregon, studying the geodynamic origins of the Columbia River flood basalts. He's a contributor to a number of software projects, including Aspects, Spleam, and ParaView. He's currently a SIG postdoctoral fellow, and we look forward to utilizing his background in teaching and software and contributing to CIG education initiatives and helping to extend Aspect to handle time-evolving anisotropic viscosity. It is the end of the week, so I am glad to hand it over to Jonathan.
Thank you. Thanks, Lorraine. Yeah, I agree. It's been the end of the week since at least Tuesday. So while I'm in my slides, I don't think I'll be able to see the Zoom screen, and I won't be able to see the chat. But I really encourage people to interrupt if you have a question. I'm happy to answer things on the fly or even sort of steer the talk to what people are interested in. And it's always a little bit hard to read the room when the room is a Zoom room, you know. So so I'm going to be talking today about some numerical models of crustal flow, specifically in the context of Yellowstone and Yellowstone's tectonic parabola. But this story involves sort of two components, and I'm going to jump from talking about Yellowstone to talking about Oregon for a little bit in the middle of the talk. And I normally hate it when people do that, but I think if I explain ahead of time that that's going to happen, hopefully I won't lose people during that transition. Oops. Okay, there we go. So Yellowstone, as most of you probably know, is a hotspot, continental hotspot in North America, located in sort of the northwest corner of Wyoming, and it's trailed by the Snake River Plain hotspot track, which sort of crosses the southern side of Idaho. And Yellowstone has long been noted to have this sort of parabola of tectonic activity around it. So this is a region that's both much more seismically active than just about anywhere else in the sort of interior of the continent. It's also hydrothermally active, and the topography in this area is much higher than the topography of just about anywhere else in the Pacific Northwest. So that represents basically this area, including the Idaho batholith up through Yellowstone itself, and then down into the Basin Range. And there are several existing stories for where this tectonic parabola comes from, or the significance or importance of this observation. The first one would be the sort of simplest explanation, just being that this is a tectonic response. And indeed, there is increased extension around that whole area. So going with the seismic activity, basically the Snake River Plain itself acts as a coherent block and doesn't deform very much. And so you would expect that extension to the north and south would cause increased uplift in those areas. Just by thinning lithosphere. This is probably the easiest hypothesis to rule out because the lithosphere is actually quite thick in all those areas, or in some of those areas, and not in the ways that you would sort of expect given just ordinary tectonic deformation. Probably the coolest of these explanations is this idea of plume flattening, which basically says that as Yellowstone, as North America propagates over Yellowstone, it's leaving behind this sort of abandoned plume head. And that plume head is spreading out underneath the continent, which is over time sort of increasing the domain of this swell, or this dynamic topography. And I think this is one of those theories that I really wish were the case, because it's really elegant, and I think it's a clever idea. But unfortunately, this is also just demonstrably not the case. So seismic images in particular really show that there is no appreciable spreading of Yellowstone, of the thermal approximately below Yellowstone as you go back in to the southwest. And so all of that sort of leaves the possibility of some sort of density perturbation within the lithosphere as the primary hypothesis for how you could generate a topographic profile that looks that's so closely correlated with the Yellowstone hotspot track. And that's conveniently supported by what's long been known to be a large, dense mafic sill in the mid-crust below the entire extent of the Snake River Plain. However, this idea is only missing sort of one component, and that's that if this were purely an added density to the lithosphere, you would expect a downwarping or flexing within the Snake River Plain. But you would expect that flexing would go all the way through the crust, and instead the moho is quite flat along this area, and even thickens a little bit off to the north in particular. So that, of course, can be fixed up by my proposed, preferred version of this story, which is that there is a density perturbation which is causing subsidence of the Snake River Plain. But that density perturbation is being accommodated by flow within the lower crust, which adjusts such that the moho is allowed to return to sort of flat state. And this has been proposed before. The first instance of this that I know of is Nadine McQuarrie back in 1998. And to my knowledge, this is probably the best supported or the most agreed upon solution to this problem, but there's very little constraint on it. So 1998 was really the most recent effort to quantify this process in a significant way. So at this point, I'm going to move to a different story about lower crustal flow in the Pacific Northwest. So we're just going to put a pin in talking about Yellowstone to talk about the Wallowa Mountains in northeastern Oregon. And I promise this will tie back into Yellowstone, but telling this story is important for telling how I get to my conclusions about Yellowstone. So the Wallowa Mountains are this anomalous mountain range in northeastern Oregon. They're anomalous for a number of reasons. One being that it's almost the only exposed granite in the entire state of Oregon. So it has a kind of unique feel to it relative to everything else around. But also the morphology of the area is just sort of strikingly unusual, that there's this little cough drop shaped mountain range that's surrounded by a ring of other smaller mountain ranges and separated by this moat of low topography, which makes up this kind of bullseye looking structure. And it's a very unusual thing to see. Sort of morphologically, most tectonic structures don't form in circles like that. Again, there isn't a well-established sort of explanation for this morphology, but probably the best explanation that I'm aware of is this idea that was proposed by T.C. Hales back in 2005, and then expanded upon by Amberly Darrell and Gene Humphreys in 2013, which says basically that something about the arrival of Yellowstone in the Miocene allowed the detachment and foundering of a dense, probably garnet-rich root from the base of this granitic pluton. So the Wallowa Mountains themselves are a Cretaceous pluton that chemically, apparently, was formed, well, at some point during its formation, a dense residuum, including a lot of the aluminum and garnet-related elements, was removed from this granite. So the interpretation here would be that you remove a dense body from the base of the crust, and that density, that loss of a dense component would produce this uplift. This is another story that is, I think, well supported, but not very thoroughly studied. And and most of the interpretations about it have been based on these sort of continental scale mantle tomography models, including the ones that I'm showing here. So a few years ago, my advisor Gene Humphreys and I and collaborators Rob Clayton and grad student Jorge Castellanos at Caltech deployed this line of seismometers from the Wallowas up to about almost to Pullman in this very dense profile, trying to investigate what the nature of the crust along this area is. So, like, is there missing crust, and what happens at this spot where you actually where we see this sort of change from a dense mantle lithosphere to no mantle lithosphere. And so this study roughly coincided in time and space to some degree with the Idaho-Oregon array, which is this line was deployed by Kathy Davenport and others. And using those data, both from the Wallowa array and the Idaho-Oregon array, plus the high lava plains and other transportable array data, Christian Stanchu formed these seismic tomographic images of sort of supporting this idea that there's a foundering dense blob below the Wallowa Mountains, and roughly what we expected to see in this area. And around the same time, also, Huilin Wang and Claire Curie used the Wallowa Mountains as a sort of example test case for this proposed mechanism of lithospheric foundering producing crustal flow that affects topography. And this study really provided a good testable hypothesis. So previously we had just been trying to resolve in higher definition the same features that we had already seen. But the prediction from this Wang and Curie paper would be that you have this channelized flow producing very highly localized strain within the lower crust. And amphibolite is mildly anisotropic, and you would expect that an aligned lower crustal mineral fabric would produce aligned seismic anisotropy within the crust. So based on this sort of idea, Jorge Castellanos at Caltech used all the same data that I mentioned before, but this time to correlate ambient noise Rayleigh waves between stations. So looking at travel time delay from station to station. If you do that with lots of different pairs of stations, you can map out the fast axis of surface wave travel times. And using particular frequency bands, so in this case it's 3 to 17 seconds, but in particular kind of centered on around 10-second Rayleigh waves. This corresponds to seismic anisotropy within the lower crust. So this is sampling depths that are between like 20 and 50 kilometers. And the results are I think, stunningly coherent, that we really didn't expect to see something on this sort of scale. That the Wang and Curie hypothesis would have predicted that you might see some sort of correlation on the scale of hundreds of kilometers. But what we're seeing here is a correlating pattern across almost 1,000 kilometers. And again, interestingly, this is all centered on the Wallowa Mountains. So all of this seems to be kind of radiating out of northeastern Oregon, or into, I guess. And one of the most fascinating parts about this is that it correlates really well with all those density structures in the upper mantle that I mentioned. So there's this anomaly, the Wallowa anomaly, as we call it, hanging below the Wallowa Mountains, and then also the Idaho curtain, which is this slab-looking feature hanging over here. And actually, if you project all these little lines out to infinity, but sort of make them decay as they move away from their station spot, and just count the crossing locations, you produce a density of line crossings that looks impressively similar to the density structure, or to the seismic velocity structure at 250 kilometers depth. So these are measurements within the crust, like 20 to 50 kilometers depth, correlating with something at 250 kilometers depth. And I just want to emphasize that this doesn't correlate with anything else. So it correlates with the mantle, and it does not correlate with anything in the crust. It doesn't correlate with terrain boundaries. It doesn't correlate with tectonic stress field, and it doesn't correlate with any sort of inherited structural deformation. It really only correlates to the mantle. Interestingly, the mantle itself does not correlate with the mantle. So if you look at the SKS splits, which basically measure an integrated sense of seismic anisotropy within the upper mantle, the seismic anisotropy of olivine in the mantle seems to mostly, can be mostly explained by the subduction zone itself. So this looks like corner flow associated with the subducting Farallon or subducting Juan de Fuca plate. And it really doesn't seem to care about the structures that I showed you here. So, so you'd expect there to be some sort of anomaly here, and maybe there's a little bit of a bend, but for the most part, the mantle doesn't seem to care about the mantle. Only the crust cares about the mantle. And this really provides an interesting new way to look at what we would normally call dynamic topography. So density structures that are mobile within the mantle are normally thought to produce uplift and subsidence at the surface because they're providing an upward or downward traction on the lithosphere. And we usually think of the lithosphere as a sort of as a filter that might elastically spread this out, but we roughly think of this force translating through the lithosphere. But this would provide a way that you could have those same forces acting on the lithosphere, but being accommodated within the crust rather than being expressed on the surface in the same sense that we usually kind of describe these things. And to first order, this actually is a really good explanation for the observations. So this is a seismic, well, sorry, this is a geodynamic model with three sort of prescribed Stokes sinkers, just dense anomalies that have been assigned to the mantle to kind of vaguely represent the structure that we see seismically. And these are acting on, well, they're within a viscous mantle, and they're acting on a low viscosity layer at the top, so a low viscosity crust. And even with this very simplified model, there's a homogeneous viscosity within the crust and three Stokes sinkers, you already produce a similar kind of radiating structure to what you actually see focused on the lavas. And of course, if you make things more realistic, you can force this to look more realistic. So if you actually take the density structures from seismic images, apply those to a geodynamic model, and use viscosity structure within the crust that's based on heat flow measurements via like a basic Arrhenius equation, you can actually produce predicted seismic anisotropy within the crust that's much more similar to the actual seismic anisotropy within the crust. So everything that I've shown you so far has been a sort of like a time snapshot of these processes, where you have forces that are acting on the crust, and you're looking at the velocity field in a sort of at that moment. And the assumption here is that velocity field continues long enough to build up a fabric, to build up some substantial amount of strain in the lower crust over time. And of course, that implies that there's long-term flow of this of the lower crust, which should rearrange the lower crust, or should thicken and thin it in important ways over time. And if you look at cross sections across the Pacific Northwest, the Columbia River flood basalts, which are Miocene flood basalts that were presumably deposited flat about between 17 and 9 million years ago, you can see lots of subsequent deformation in those basalts. So well-dated deformation. But if you look at this through the lens of looking for crustal flow signatures, you can find all kinds of bizarre features in here that you really wouldn't expect to find through normal tectonic deformation. So you can find folds that are perpendicular to other folds, or things that really shouldn't make sense if you were only deforming things in a horizontal sense. And I made this tool that you can use online through this URL, which I'll post in the chat later during questions. But this is an interactive tool where you can go look at all these maps that we digitized of Columbia River flood basalt contact, and you can see all kinds of really bizarre features in here. Very cool. I recommend checking that out. Okay, so in addition to seeing this in geologic cross sections, you can also just see it in the topography. In particular, one of my favorite examples is this area just to the north of the Wallowa Mountains. So these are the Wallowa Mountains. This is Enterprise, Oregon, and Joseph, Oregon. There's Highway 3 goes up this valley right here. This is called Trout Creek. And at some point around here, Highway 3 cuts up onto this plateau and continues. But if you were to continue going up this valley, you would eventually reach a drainage divide. But it's a very unusual drainage divide because it lies within what appears to be a continuous valley. So it looks very much like there should have been continuous flow going through this valley one direction or another. And you can actually find gravel deposits down here in Trout Creek that show that this stream did indeed flow to the north previously, and now it's split. So part of it is flowing to the south and part is flowing to the north. And even as a non-geomorphologist, this is another one of those things that just looks wrong, I guess. It doesn't look the way you would expect. So this is Enterprise, Oregon. This is Trout Creek, just following the path of the stream. And if you zoom in on that drainage divide, I think you'd have a hard time pointing to where it is. So it turns out that it's right in the middle of this field right here, but you would never know that just standing in this field. This valley looks continuous. There's nothing obviously different about this spot than anywhere else. And there's even like recent sediment deposits here, which you would normally not expect to see at a drainage divide. But of course, also in the framework of lower crustal flow forming changing topography, this makes perfect sense. We sort of expect that there's been an evacuation of lower crust from the Wallowas themselves, which would tend to thin out the crusts in the kind of near field and leave the crusts thicker in the far field. And this is where I can finally get back to Yellowstone and mention that we see these same signatures in Yellowstone. So we see all the same things. So structurally, there are these normal faults associated with basin and range extension on both the north and the south side of the Snake River Plain. You can follow strata along these ridges that just dive down underneath the Snake River Plain and pop back up on the other side. So vertical deformation. And interestingly, you see the same sort of unusual drainage divides within these valleys between the normal faults here. So this is actually maybe not the best example because it crosses a separate fault, but if you zoom in here, you see a kind of similar thing with like recent sediment deposition at this drainage divide, and no obvious reason that you should have a drainage divide there at all. So I think to sort of emphasize that point, these are normal faults that roughly begin here and end here, at least in their surface trace. With a normal fault, you would expect the highest throw in the fault to be right in the middle of the surface trace. And at that spot, you would expect there to be a depositional basin. So think like Salt Lake City and the Wasatch Front. And in this case, rather than having a topographic low accumulating sediment here, you actually have a topographic high, which is shedding sediment to either side. So this is what I've been calling an abnormal fault. And you can find them all over the place, especially associated with Yellowstone, and there are some around the Wallowas as well. again, this makes perfect sense in the framework of lower crustal flow, that we've evacuated crust from below the Snake River Plain itself, and we've inflated the surrounding terrain. So we've thinned out the crust below the Snake River, and we've thickened the crusts below these mountain ranges. And in sort of the opposite sense of what I explained in the Wallowas, the Wallowas are a negative pressure below the Wallowas that are evacuating crust or sucking crust in from the surrounding regions. Here we have a positive pressure perturbation that's ejecting crust into the surroundings. So we would expect that if this crust is relatively viscous, it would tend to build up a topographic high here. So you think of like, I don't know, squishing a toothpaste tube, you would expect that you develop some sort of bulge in the near field. And that over time that bulge might start to diffuse out or to flatten out just due to its own gravitational potential energy. So the process, that process is very dynamic. So in the case of the Wallowas of the Trout Creek that I showed before, you sort of expect that bend to happen in Trout Creek at about the place that it happens. But here you might expect that this system would be changing through time. So you might expect that the drainage divides there might be migrating away from the Snake River Plain over time. And this is something that's been proposed before outside of the context of lower crustal flow, but Carl Wegman and others have proposed that if you filter topography using some like Gaussian filter, what you're seeing is roughly the flexure or the topography that the landscape wants to have given some sort of dynamic effect. And then if you look at the actual drainage divides compared to those sort of predicted drainage divides, you can see, well, there must be some sort of reason that this used to be the preferred place for drainage divides to happen. But now you would expect that these ridges or these divides would be moving outwards to sort of adjust to this this filtered version of the topography. So to simulate this kind of time evolving process, we need a model that's more complex than the time independent ones that I've described so far. So we need to not only look at an instantaneous snapshot of flow, but we need to be looking at how does this flow evolve over millions of years. And we would really like to be able to test that on lots of different combinations of model parameters. But if we were to do that for many millions of years in a three-dimensional lower crust, we would, that would be technically very challenging. So we would be wasting a lot of computational effort on that process. But fortunately, what we actually have here is we're already assuming this sort of channelized Poiseuille flow style flow profile, which can be equally well described by simply noting what the highest velocity is, so the velocity at the middle of this channel, and also how thick the channel is. And given those two pieces of information, you can predict what the rest of this flow field is just given those pieces of information. And that allows you to reduce the problem's dimension from being a three-dimensional, or I guess in this cross-sectional image, this would be two-dimensional, would go down to a one-dimensional problem where you're only looking at flow along this midplane. And we can actually reformulate the flow laws to account for that. Most notably adding, well, actually subtracting a linear relationship with the velocity itself. That sort of represents the fact that even given no gradients in velocity in map view, you can still be dissipating energy just by flowing through this kind of parabolic structure. So this allows us to map out huge swaths of parameter space by running models over tens of millions of years with a huge range of different parameters. So in this example, a similar thing to the Snake River Plain, adding a load and looking at these topographic divides to either side of the lode, you can measure things about these topographic divides and say like how quickly are they migrating, and how quickly are they uplifting in this example. And you can do that for models running over 15 million years each, for hundreds or maybe even thousands of models within a couple hours on a normal computer, because these are just one-dimensional finite element models. And in this case, if you look at ranges that are actually appropriate for the lower crust, you see that there are a number of cases, probably like about half of the cases within this model space, where you actually do have significant amounts of uplift and significant rates of migration. So these are cases where you have this divide both uplifting and migrating at the same time. And of course, you can also do this in like pseudo 3 dimensions, so in a 2-dimensional sense, but with the 3rd dimension sort of implied. And you can watch what happens if you just slide basically a propagating like hockey puck of emplacement, adding dense sill material to the mid-crust, and moving across this model. You can see flow propagating along here. And in time, you can actually see this producing this kind of this bow front and then this wake off to the sides, which looks quite a bit like the description that I gave at the beginning of the tectonic parabola. However, there are a couple problems with this result. So one is that that topographic bulge decays over time to the point where back here you have basically no bulge at all. It just gets very small. What's happening is roughly that you build up this this sort of shock front, and then it diffuses out over time, and eventually the topographic signature just goes away. And that's really not what we see in the snake river plain. We also really don't see, despite this being called the tectonic parabola, it really doesn't spread much over time. This is really a tectonic hyperbola or something at best. It seems to sort of bow around Yellowstone Park and then basically runs parallel to the Snake River Plain. And when we look at other sort of indicators of the rate of migration of drainage divides, including this one, which is the difference in topographic relief across drainage divides, we see differences in topographic relief across these ridges themselves. So from one side of the ridge to the other. But in the valleys that separate the ridges, we really don't see very much, if any, sort of what would indicate instability in this ridge location. So it seems like these ridges are presumably moving some amount, but not substantially, not very fast. And places like this, where there is a big gap, this has more to do with the structural fabric of the area, where you have these normal faults that are separating kind of northwest, southeast, like in this periodic structure. So what would happen here if you breached this small drainage divide, then suddenly this black line would jump over to be almost exactly on top of the purple line. And lastly, the observations also don't support this idea of a sort of transient pulse of uplift. As part of this project, our collaborators at Indiana University and University of Washington collected a bunch of cosmogenic samples from both the Clearwater and Salmon watersheds in northern Idaho. And we were looking for some sort of signal of southern Idaho, or the kind of central northern Idaho, uplifting first, followed by a sequential like propagation of uplift into northern Idaho. But instead, what we found is more consistent with just an overall tilting of northern Idaho in this kind of trapdoor shape, which which again really isn't consistent with this idea of a sort of like squishing a toothpaste bottle or tube and then seeing this pulse propagate away. And I think really what's missing here is that the upper crust is affecting this system. So the upper crust is behaving as an elastic filter that has a sort of preferred bending length. It'll, if you weight one side of it, it will tend to, you'll produce a bend, and the lower crust will adjust to that preferred elastic bend, but you won't develop this kind of purely viscous response. So if we include that elastic filter on here as well, so couple the elastic plate to the flow of the lower crust, we actually do end up getting something very similar, where if we look at a sort of cross section of this system, applying a load to the center, we see uplift producing these bulges that are affecting far field at the same time as they're affecting near field. And what ends up happening is that you sort of inflate these areas with more crust, but they all uplift roughly at the same time. You get more uplift nearby and less uplift away, but the flexure is really what's controlling the pattern of uplift and not so much the flow. In a time evolving sense, that looks something like this. This particular model doesn't have a very strong elastic upper plate, so those flexural bulges are relatively small, but you still get the sense here that you develop these flexural bulges that sort of stabilize with time. They don't just diffuse away in a kind of viscous, sense. And so including that elasticity of the upper plate, doing the same sort of hockey puck emplacement along the continent, you do see that sort of what we would expect to be a more parallel ridges develop along the edges of the Snake River Plain, or along the plain in this case, preceded by this sort of arc of uplift ahead of the plain, or ahead of the plume head. Okay. I'll try to wrap up soon so that we can do questions. We'll give it another 5 minutes or something. All right, so so again, pseudo 3 dimensions, we end up getting this kind of these parallel ridges to either side of the propagating hotspot. And this is much more consistent with the uplift that we've observed, and also with the other indicators of surface processes. But one additional path that we can take that's still sort of in its infancy, I don't know, developed by Brian Unitas and Nate Mitchell at Indiana University. They're taking the outputs from the model that I showed you with predicted uplift rates, and applying those as an uplift field to surface process models. So looking at how erosion will modify this landscape based on the uplift patterns that we observe, or that we predict from these crustal flow models. And again, this is one of those things that we've only started. So we haven't done an exhaustive parameter search to find one that best fits Yellowstone. And these are mostly based on a sort of arbitrary model output that we produced. So using numbers that are similar to what we expect for Yellowstone, we were able to produce a kind of uplift signature that looks roughly consistent with what we actually see. So what's happening here is that initially start with some sort of steady state landscape and start uplifting these ridges at some preferred distance. And you get this sort of propagating wave of uplift but it very quickly kind of chooses a distance or a preferred wavelength that it likes, and then it'll just sort of erode into that, kind of maintaining the same structure over time. And in map view, it looks roughly like what we actually see, where you have this these sort of sharp, like steep-sided valleys, or this uplift that's very steep on the Snake River Plain side, and then sort of more gentle towards the outer edge. And again, trying to match this with the modern topography, what we see in cross-sectional swaths along this kind of north-south profile, from our predicted uplift has a similar form to the actual uplift. Again, this model is somewhat arbitrarily chosen, and presumably testing a wider range of model parameters would actually get us closer to the real system. But we do see this steep-sided valley, sort of with this long decreasing topographic profile to the other side. And this gets me to my last point, which is that all of this really requires more like self-consistent coupling. So if we're going to be doing something where we impose uplifts from one model onto another model, we need those uplifts to propagate back into the original model. So in this case, all that's happening is the uplift rates predicted by the crustal flow model are informing a surface process model. But that surface process model isn't talking back the other way and telling the crustal flow model to adjust its isostatic response and so on, and it's not depositing sediments anywhere. And that also gets at the point that there are really two sides to this problem. So I described in the Wallowas case, we have a bottom-up system where we have forces in the mantle acting on the lower crust. And in the Yellowstone case, we have forces in the upper and mid crust acting on the lower crust. And so all of this is going to require coupling in both directions. So both from surface processes, mid-crustal volcanism or sort of magmatic emplacement, but also from the geodynamic side. So, so the forces that are generated within the mantle are going to have to affect this crustal flow in one way or another. And that's sort of one of the other directions that this project is hopefully going to go in, is figuring out a way to couple a two-dimensional finite element model with a three-dimensional finite element model, hopefully across like parallelized model runs with adaptive meshes and all that stuff. And preliminary efforts at this are kind of promising that I'm able to actually produce a mesh that is the same across a two-dimensional model and a three-dimensional model, but the two-way coupling is still something that needs to be finished. All right, actually perfect timing. I'm going to leave it there and I'll take questions. And I'm happy to go into more depth on whatever one of those various topics people are most interested in.
Great, thank you so much, Jonathan. A lot to think about with regards to the crustal deformation in that area. I have sort of a new appreciation for its complexity, but that was a nice story. If you have a question, lots of different ways to do this. You're probably all familiar with it, so just either turn your camera on or type something into the chat. I will start us off while you guys are all getting warmed up out there. What is sort of the role of normal faulting in your models?
So in my models don't account for horizontal tectonics at all, really. So there's not extension in them, which is something that will be important. It's one of the things I didn't mention so much, but one of the kind of most notable things about this tectonic parabola is that it's much more distinct on the north side than it is on the south side. And I think that has to do with the fact that there's much more extension on the south side than there is on the north, and that's something we're not accounting for.
It seems like there's a large component of normal faulting that could affect the models in multiple ways.
Yeah, especially when comparing with surface processes, that's something that really needs to be addressed. Like I mentioned down here, there's this spot where the modern topography doesn't seem to be in line with what the filtered topography wants it to be. But that's like a hair away from jumping like tens of kilometers just because you have these normal faults really defining the landscape.
Tahiri.
Hi, Jonathan. Thank you for the nice talk. I have a question regarding the flow law that you use for the crust.
Mm-hmm.
Do you use creep law, what composition, and also like, do you consider the formation of the fabrics, the seismic anisotropy, when during, like, how does it, do you consider like a feedback to the viscosity, or?
At this point, no, but it's something that's possible with, so I should mention that the code that I used for those is available on GitHub, and is part of the publication that's in review right now. And all of that is very much possible. So right now, viscosity is just defined as a number that can be spatially variable, and it can vary in time. But in the models that I showed, all that's happening is they all have a constant value of viscosity everywhere.
Okay.
And those are sort of informed by mineral physics, but they're really just guesses, and they're uniform, so they're not developing any sort of preferred orientation over time or anything like that.
Thank you.
Other questions? In a couple of your slides, you show the current and the predicted drainage divide along the eastern Idaho. What is that telling us about sort of the response time to I guess the mantle and upper crust response time to forcing parameters? I mean, there must be something that tells us about length and time scales there, right?
Yeah, I think that, well, part of me is just skeptical of this as a method for really measuring how stable a landscape is. I think that this idea that the landscape ought to conform to some sort of filtered version of itself is clever, and I think it's neat that this does seem to imply that this ridge ought to be migrating that way. But I'm really, I don't know, I'm not a surface process person, but I'm a little bit skeptical to put too much weight on really believing whether or not this actually represents a transient landscape or if it's just sort of a coincidence. Does that answer your question? I don't know if that was even like...
Yeah, that answers the question. I have to say the Wallowa Mountains look very beautiful.
Anyone who hasn't been there, I highly recommend it. It's very cool.
Hi, Jonathan. Yeah, thanks for the talk. I was wondering, could you remind me what was the maximum flow velocity that you got in the channel, the pressure-driven flow?
In the, let's see. In the original one, in the sort of instantaneous sense, the maximum velocities I got were on the order of like 1 millimeter per year.
Oh, okay. And for the hockey puck moving object?
I don't have, let's see. Off the top of my head, I don't remember what the maximum velocities of flow were. I can tell you that the maximum uplift rates that I got were on the order of like 0.05 millimeters per year or something like that.
Okay.
But the flow rates, I'm trying to see if I have a figure that shows them. Yeah, I don't have a figure that shows that. But the flow rates are much harder to constrain anyway. The uplift rates are much more indicative of anything physical, I think, or easier to match to data.
Okay. Do you have a sense for how it would compare to the actual plate velocity at that time?
Oh, that's an interesting question. That's something that, so in those hockey puck models, the ones that I showed were, so in all cases, I think that the crustal flow is going to be slower than plate velocity, which is interesting because that's sort of what causes that like almost shock wave in front of that intrusion. Like it basically doesn't have time for flow to outrun the plate.
Right. Okay. Cool. Thanks.
Yeah.
Emmanuel.
Hi. Wow, great talk, Jonathan. First question, I wish to ask, how deep does your model goes? And then does it account for the foundering or sublithospheric structure that is sinking?
Okay, so there are sort of two models here. There's this one, the one that's looking at flow driven by the mantle, and in that case, that's a whole mantle model, but it only includes density structures from this little square. So it's not including like a global mantle tomography model. It's just including these structures. But then the Yellowstone model is only a top-down model. So while this model is missing the surface process and the upper mid-crust processes, the Yellowstone model is missing the mantle components. Was that your question? I might have misunderstood it.
Yeah, seeing you say it's missing the mantle components, like, yeah, I was like asking how deep does your model, like the maximum depth you're modeling? I know you're focused on lower crustal flow, but so I was asking how deep does it go, and do you account for a sinking or a foundering sublithospheric component?
Yeah. Okay. Yeah. So yeah, the answer really does depend on which model it is. So the Yellowstone model is roughly meant to represent the structure that's seismically imaged within the mid and upper crust. So that model goes down to, I'm trying to see if I have a better image of this, but it's based on existing tomographic models of the crust. So going down to like 40 or 50 kilometers. But the one that encompasses the whole region, the one that's this model, this one includes all the way down to the core mantle boundary.
Okay.
So for those of you interested, I did paste into chat the link to the Columbia River Basalt Explorer. It's a fun little tool. I don't know if Jonathan wants to take the last 5 minutes and show off it. It's a nifty little tool that you can create cross sections through the Columbia River Plateau basalts. It can be a fun sort of teaching and outreach tool for anybody who's looking for such a thing.
Yeah, definitely. This is that's it. Oh, what was the link?
It did that to me too. I had to go through your repo directly.
Yeah.
You can probably click on the link in chat, might get you there.
Oh yeah. Well, I do have this animation of it.
Yeah.
But the yes, I highly recommend this as a teaching tool, but also just as a fun thing to play with. I think you'll be surprised what you find in it. Even if the CRBs are not your main interest, I think that you can learn some interesting stuff about the Pacific Northwest from this.
Yeah, it's much more complex than I thought. I've driven through there and I had a very planar view of the world.
Yeah, so especially if you've driven through the center part, it's very flat.
Yeah.
Yeah. But some of these parts, like down here, are much more complicated.
Yeah.
The really powerful thing about this tool is that you can spread out that cross section and then you can tilt it in 3D. And you can explore sort of, yeah.
This is really cool. That's really cool. Okay. Last chance to get in any questions for Jonathan. This presentation and slides will be posted shortly. This is the only officially scheduled CIG webinar for the year, but we are joining forces with Seductions and 4D as well as CSDMS to present a seminar series, and I hope that will be out. That announcement will be out shortly, I hope. So stay tuned. Happy holidays. Have a good AGU, and of course, stay safe. And thanks once again, Jonathan, for a really great talk.
Yeah, thanks everyone for joining, making the time.